Lesson 23, the photoelectric effect. Quantization of light, or wave-particle duality. We've learned in the past that light acts like a wave. It reflects, refracts, diffracts, and it interferes with itself. But we also have learned that light acts like a particle. It comes in packets of energy that can't be broken apart. The particle of light is called the photon. Wave-particle duality means that light is both a wave and a particle at the same time. This all came from Planck's discovery. Planck discovered that photons are particles of light, and the energy of a photon is given by Planck's constant times the frequency of that photon. Planck's constant comes in two forms. It's either 6.63 times 10 to the negative 34 joules seconds if you're wanting your energy measured in joules. Or it's 4.14 times 10 to the 15 electron volts seconds if you want your energy to be measured in electron volts. This is Planck's formula for the energy of a single photon in a beam of light with a particular frequency. Part 1. The photoelectric effect problem. In 1887, Heinrich Hertz discovered the photoelectric effect. Here's a picture of Heinrich Hertz. In the photoelectric effect, it was discovered that when light is shone on a clean metal surface, electrons are emitted from that metal. Throughout the 1890s, the photoelectric effect was studied using cathode ray tubes. Cathode ray tubes are vacuum tubes, which means they've removed all air from inside the tube, and with two metal electrodes on each side. Electrodes are just pieces of metal, and in this case, they're placed one on each side. If they are connected to a battery, a beam of electrons will flow from the cathode to the anode. The first cathode ray tube was built before the discovery of the electron. At the time, the glowing beams of electrons were a mystery to science, and since they came out of the cathode, they were called cathode rays, hence the name cathode ray tube. For the photoelectric effect in a cathode ray tube, light is shone on the cathode, and if the light has enough energy, electrons are released from the cathode. These electrons are sometimes called photoelectrons because they are released by light. Photo refers to light. The flow of these electrons is called photocurrent. If a beam of light is shone on one of the metal electrodes, and that beam of light contains enough energy, the metal electrode will release a beam of glowing electrons, and the electrons will flow from one electrode to the other through the cathode ray tube. We call the cathode the electrode that the electrons are released from. The anode is the electrode that the electrons travel towards. When Hertz studied the photoelectric effect using a cathode ray tube, four properties of the photocurrent, or the electron beams, were discovered. First, a substance emits electrons only if the light has a frequency above a threshold frequency. The symbol we write for this is F for frequency, naught to indicate that it's the beginning or the threshold frequency. Different metals have different threshold frequencies. For example, zinc will emit electrons for violet light, but not for blue. Second, once the threshold frequency has been reached, the electrons flow instantaneously. They start flowing right away. Third, increasing the intensity means brightness, of the light, increases the amount of electrons released. And fourth, increasing frequency past the threshold frequency increases the kinetic energy, which means it increases the speed of the emitted electrons, but it does not change the amount of electrons released. From the classical physics point of view, where light is an electromagnetic wave, when light is illuminated on the surface of a metal, electrons in the metal are violently shaken and oscillated by the vibrating electromagnetic field of light. So the electrons start to bounce around in the metal when the light wave lands on them. But this is the classical physics point of view. Classical physics could almost explain the photoelectric effect. If the oscillation was too great to keep the electrons inside the metal, they would jump out of the metal surface. but it couldn't explain any of the other features of the photoelectric effect. According to classical physics, the energy given to the electrons is proportional to the square of the strength of the electromagnetic field. Hence, the maximum energy of the photoelectron must be dependent on the intensity of the light illuminated, which completely contradicts Hertz's experimental results. In other words, classical physics predicts that the kinetic energy of the electron should be proportional to the intensity of the light, but this is not what Hertz found in his experiments. Part 2. Einstein's explanation of the photoelectric effect. The fact that classical physics couldn't explain Hertz's discovery when he was studying the photoelectric effect was troubling to scientists. It wasn't until Albert Einstein came along and offered an explanation that they were able to explain mathematically all the results that they had discovered. Einstein used Planck's constant of particles of light to explain the photoelectric effect. Planck explained that the energy of a single photon can be predicted by its frequency, where energy equals Planck's constant times the frequency. Einstein explained that photons of light, single particles of light, travel towards the metal surface. Each particle had an energy equal to hf. The electrons had a particular amount of energy that would allow them to be released. We call this particular amount of energy the work function. If the energy of the photon was less than the work function, the electron would not be released. If a photon came in with more energy, and that energy was greater than or equal to the work function for that particular metal, the electron would be released. Here's how Einstein explained the photoelectric effect using photons. The threshold frequency. Each electron is bound to the metal's cathode by a unique amount of energy called the work function. We use the symbol W to show the work function. Work function is just a type of energy, which means the work function is measured in joules. The fact that the photocurrent is instantaneous can also be explained. If a photon has energy greater than the work function, the electron will be released. If the energy is less than the work function, the photon will be absorbed and nothing will happen. Einstein explained the increasing intensity. Changing light intensity means we've changed the number of photons in the light. More photons means more electrons can be released. Finally, Einstein was able to explain the increasing frequency. Increasing frequency changes the amount of energy each photon has, but does not increase the number of photons in the light beam. Since one photon releases one electron, increasing frequency does not change the number of photons that can be released. Any extra energy after the threshold energy that's given becomes kinetic energy for the released electrons. Think about it like this. The work function, or the threshold frequency, is like the price at a shop. If a customer has enough money, they will be given the product right away. If they don't, they'll go home empty-handed. More customers means more products are sold. If each customer has more money in their pocket, they don't necessarily buy more products. How many things does a person actually need? They go home with the product and more change to spend somewhere else. Einstein developed the following formula for the photoelectric effect. He said the kinetic energy of the released electrons is equal to the energy of the photons that fall on it minus the work function of the metal. You can imagine this formula working like this. Imagine that you're in jail, which means you're trapped behind bars, and your bail is set at $1,000. The bail is like the work function of the metal. Your grandma comes along, and your grandma loves you so much, she brings $1,300. This is like the energy of the photons that fall on the metal where the electrons are trapped. Then, because your grandma comes with enough money to release you for bail, you are freed. But more than that, you have an extra $300 to spend, so you can go buy yourself a new pair of shoes. This is like the kinetic energy of the electrons once they're released. The kinetic energy of the electrons is equal to the energy that the photons bring with them, minus the amount of energy that was required to release them in the first place, the work function. If the threshold frequency required for the emission of a photoelectron is 4 times 10 to the 14 hertz, what is the work function of the surface in joules and electron volts? In this example, we're given the threshold frequency of 4 times 10 to the 14 hertz. We use the formula work function equals HF. Since we want to get this in joules and electron volts, we use the Planck's constant for joules first, 6.63 times 10 to the minus 4 times the threshold frequency of 4 times 10 to the 14 hertz. This gives us a work function equal to 2.65 times 10 to the negative 19 joules. Converting this to electron volts, we remember that 1.6 times 10 to the minus 19 joules is in every electron volt. So 2.65 times 10 to the minus 19 joules times 1 electron volt divided by 1.6 times 10 to the minus 19 joules. Joules cancels out, and this gives us a work function in electron volts equal to 1.66 electron volts. So we know that if a photon with energy equal to 2.65 times 10 to the minus 19 joules, or 1.66 electron volts, falls on the metal, an electron will be released. Example 2. Gold has a work function of 5.1 electron volts. What is the speed of an electron released if light with frequency of 2.5 times 10 to the 15 hertz is shone on it? The work function of the metal is given as 5.1 electron volts. We are also given that the frequency of the photons falling on the cathode is 2.5 times 10 to the 15 hertz. The kinetic energy of the released electrons is equal to the energy of the photons that fall on it minus the work function of the metal. The energy of the photons is Planck's formula, HF. So the energy kinetic is equal to Planck's constant 4.14 times 10 to the negative 15 times the frequency of 2.5 times 10 to the 15 minus the work function of 5.1 electron volts. This gives us a kinetic energy in electron volts of 10.35 minus 5.1 equals 5.25 electron volts. We're going to convert this into joules so that way we can calculate the velocity. 5.25 electron volts times 1.6 times 10 to the minus 19 joules in 1 electron volt. Electron volts cancels out and leaves us with joules. So we have the kinetic energy of our photons equal to 8.4 times 10 to the negative 19 joules. Kinetic energy is 1/2 mv squared. So V is the square root of 2 ek over m. The velocity of the electrons is equal to 2 times the kinetic energy, which is 8.4 times 10 to the minus 19 joules, divided by the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms. All this square rooted. This gives us a velocity of the released electrons of 1.36 times 10 to the 6 meters per second. And on to our third example. A metal surface has a work function of 2.06 electron volts. If the fastest photoelectron emitted from it is 6 times 10 to the 5 meters per second, what is the frequency of the light source striking the surface? So we're given the work function of 2.06 electron volts. And the velocity of the photoelectrons is 6 times 10 to the 5 meters per second. The first thing we'll do is turn this velocity into a kinetic energy. Kinetic energy is 1/2 mv squared. So this is 1/2 the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms, times the velocity of the electrons, 6 times 10 to the 5 squared. This gives us a kinetic energy equal to 1.64 times 10 to the minus 19 joules. But since our work function is given in electron volts, we'll convert this kinetic energy into electron volts for simpler calculations later. 1.64 times 10 to the minus 19 joules times 1 electron volt divided by 1.6 times 10 to the minus 19 joules gives us kinetic energy equal to 1.025 electron volts. We know the kinetic energy of the escaping electrons is equal to the energy of the photons falling on them minus the work function of the metal. We can rearrange this for the energy of the photons that fall on it. Energy of photons equals Ek plus the work function. Since the energy of the photon, given by Planck's formula, is hf, we can write hf equals Ek plus W. And if we divide this by h, we get F equals Ek plus W divided by Planck's constant. This gives us 1.025 plus 2.06 Ek plus W divided by Planck's constant for electron volts, 4.14 times 10 to the minus 15, which gives us 7.45 times 10 to the 14 hertz. Fourth example. If a metal surface has a threshold frequency of 4 times 10 to the 14 hertz, what is the kinetic energy of the escaping photoelectrons when light with a frequency of 6 times 10 to the 14 hertz strikes the surface? We're given a threshold frequency of 4 times 10 to the 14 hertz and a frequency of the incident light equals to 6 times 10 to the 14 hertz. Einstein's formula tells us that the kinetic energy of the escaping electrons is equal to the photon energy minus the work function. The energy of the photon given by Planck's formula is hf. The work function is hf naught, or the threshold frequency. So Ek equals hf minus hf naught. And since h appears in both terms, we can factor it out, go hf minus f naught. This gives us Ek equals 6.63 times 10 to the negative 34 times 6 times 10 to the 14 minus 4 times 10 to the 14, which gives us a kinetic energy of the electrons equal to 1.33 times 10 to the negative 19 joules. Part 3. Millikan's photoelectric experiment. In 1915, Millikan experimentally verified Einstein's equation. Einstein's equation is Ek equals the energy of the photons minus the work function. And he also measured Planck's constant. He hooked up a variable voltage to the cathode ray tube and measured the voltage required to stop the electrons. So if this is the cathode, and this is the anode, he hooked up a battery, so the negative terminal of the battery was connected to the anode. This made the anode negatively charged. As a result, the electrons approaching the anode saw the negativity of the anode and turned around and went back to the cathode. This was called the stopping voltage, or V stop. It was the voltage that was required to stop the electrons from flowing to the cathode to the anode. He reasoned that this stopping voltage represented the electron's kinetic energy, since voltage is equal to energy divided by Q. The energy of the electrons would be equal to Q times the stopping voltage. EK equals QV stop. For example, when 193 nanometer light is shone on zinc metal, a photocurrent of 0.228 amps is measured. If the battery voltage is adjusted to -2 volts, the current is stopped. What is the work function for zinc? Let's look at an animation that summarizes this. As the light is increased in frequency, eventually the light will reach the threshold frequency, which will cause the electrons to be emitted at about 243 nanometers. We bring the slider all the way to 193, and we start adjusting the voltage to 2 volts. At 2 volts, the current stops and hits 0. So in this problem, we're told that the wavelength incident on the photons is 193 nanometers. This means the energy of the photons is HF, and since F is equal to C over lambda, the energy of the photons is equal to hc over lambda. This gives us an energy of the photons equal to 1.0306 times 10 to the negative 18 joules. We're also told the stopping voltage for the electron beam is equal to -2 volts. I'm just going to write this as 2 volts, the absolute value, because the negative refers to the charge and not the direction, and I don't want to confuse things. The kinetic energy is equal to the charge of the electron times the stopping voltage. This is 1.6 times 10 to the -19, which is the charge of an electron, times 2 volts. This means the kinetic energy of the electrons as they escape the metal is 3.2 times 10 to the -19 joules. We can use all this to calculate the work function. Einstein's equation says the kinetic energy of the escaping electrons is equal to the energy of the photons minus the work function. This means the work function is equal to the energy of the photons minus the kinetic energy of the escaping electrons. This is 1.0306 times 10 to the -18 minus 3.2 times 10 to the -19. This gives us a work function equal to 7.1 times 10 to the -19 joules. Electron volts are sometimes easier to use when working in the photoelectric effect. For example, for the previous example, we were told that the stopping voltage is 2 volts. By definition, the energy in electron volts is the energy one electron would experience in 1 volt of charge. So let's calculate the energy of these electrons in electron volts. The kinetic energy is Q V stop. This is equal to 3.2 times 10 to the -19 joules. But if we convert this into electron volts, which means that we divide 3.2 times 10 to the -19 joules by 1.6 times 10 to the -19 joules in electron volt, this gives us 2 electron volts of energy. So if we take 2 volts to stop the electrons, that means the electrons have 2 electron volts of kinetic energy. Using his measurements, Millian produced a graph of the kinetic energy of the electrons as a function of the frequency of the incident light and obtained a linear graph that looked something like this. Einstein's formula is EK, the kinetic energy of the photoelectrons, is equal to the energy of the incident photons, which is HF, minus the work function. Since we've plotted EK versus frequency, we can compare this to the linear equation, y equals mx plus B. On this graph we've plotted the kinetic energy is on the y-axis and the frequency is on the x-axis. This suggests to us that the slope of the graph is equal to Planck's constant and the y-intercept is equal to negative of the work function. If we examine the graph, the spot where the kinetic energy of the electrons is 0 is the place where the frequency is equal to the threshold frequency, and that's at the x-intercept. So we find the x-intercept is the threshold frequency, the y-intercept is negative of the work function, and the slope is equal to Planck's constant.